Aloha. In AI, there are at least five major schools of thought: symbolism, connectionism, Bayesianism, analogism, and evolutionism. This video provides a brief introduction to two of the most prominent: symbolism and connectionism. Symbolism and connectionism have competed, evolved, and even intertwined over the decades, each offering unique perspectives on how machines can mimic human intelligence. This video explores the history, principles, and interplay of these two schools. Imagine a world where intelligence is neatly structured, a place where knowledge is carefully encoded into symbols and manipulated through logical rules. This was the dream of early AI pioneers like Alan Newell, Herbert Simon, and John Shaw. In the 1950s and 1980s, the symbolic approach dominated AI research, emphasizing structured reasoning. One of the earliest breakthroughs was the development of the Information Processing Language, IPL, and the logical theorist, a chess-playing AI that could make strategic moves by following predefined rules. The general problem solver, GPS, soon followed, aiming to solve a wide range of problems using symbolic reasoning. The cornerstone of this approach came with Newell's physical symbol system hypothesis, which argued that intelligence must be based on processing structured symbolic representations. A key extension of symbolic AI was John Anderson's adaptive control of thought rational model, which proposed that our minds operate through a combination of declarative, factual, and procedural, rule-based knowledge. This idea built upon Newell's framework, but added psychological realism. However, while symbolism excelled in rule-based problem-solving, it struggled with ambiguity, learning, and adaptability, shortcomings that connectionism sought to address. In contrast to the rigid logic of symbolism, connectionism took inspiration from the brain's neural networks. Instead of encoding knowledge into structured rules, connectionist AI learns from patterns in data, much like how humans recognize faces or understand language. The term connectionism was coined by psychologist Edward Thorndike in the early 20th century. Early neural networks, like Frank Rosenblatt's perceptron, hinted at the potential of machine learning. But it wasn't until the 1980s that AI researchers found ways to overcome their limitations. A breakthrough came from the Parallel Distributed Processing (PDP) group in California, where researchers like David Rumelhart and Geoffrey Hinton refined the backpropagation algorithm. This innovation allowed neural networks to self-adjust by continuously tweaking their internal parameters, leading to dramatic improvements in tasks like image recognition and speech processing. Hinton, heavily influenced by Donald Hebb's learning theory, continued advancing the field with architectures like the Boltzmann machine and later the capsule network, which improved AI's ability to recognize hierarchical relationships in data. Today, thanks to connectionist advances, AI can power everything from virtual assistants to self-driving cars. Due to his significant contributions to AI research, Hinton won the Turing Award in 2019 and the Nobel Prize in Physics with John Hopfield in 2024. A major difference between symbolism and connectionism is that in the former concepts and symbols are one-to-one correspondences, whereas in the latter, a single concept can be represented by numerous neurons, and a neuron can carry information of different concepts. As such, symbolism is limited by the fact that notations must be logically connected in a rule-based system. For example, if A1, then do B1, else if A2, then do B2, else do B3, etc. Specifically, the symbolic approach is a production system which consists of a set of rules or productions for deriving new information from existing information. However, it is difficult, if not impossible, to build a comprehensive production system that includes millions of rules. Indeed, no system can exhaust every existing concept or event in the world, let alone new cases. As a consequence, the computer system may not know what to do while encountering a new scenario that is never encoded. In contrast, connectionism is an example-based or knowledge-based system that is capable of handling new information through pattern recognition. Another major difference between the two approaches is that the former is confined to sequential processing, while the latter can utilize parallel processing. In a symbolic system, deduction is implemented in a step-by-step fashion. For instance, if A, then do B, if B, then do C, if C, then do D, etc. But using the connectionist approach, all neurons learn at the same time following Hebb's law. Today, serial computing is limited, whereas high-performance computing for AI and big data analytics must be parallel processing. Nonetheless, connectionism also has several limitations. For example, connectionist models often struggle with tasks requiring explicit reasoning and causal understanding, lacking the interpretability needed for validation and trust in decision-making processes. The substantial computational resources and extensive labeled datasets required for training connectionist models can limit their applicability, particularly in data-scarce environments, posing practical challenges. Training large-scale models like GPT demands GPUs, TPUs, or specialized hardware, making them expensive and energy-intensive. While symbolism dominated early AI and connectionism later took the lead, researchers have increasingly explored ways to merge the two. Instead of viewing symbolism and connectionism as rivals, modern AI research has sought to combine their strengths. Hybrid models aim to integrate symbolic reasoning with connectionist learning, creating systems that can both learn from data and reason logically. For example, in 2019, a group of researchers at MIT introduced the neurosymbolic concept learner, which applies deep learning for pattern recognition while incorporating symbolic reasoning for logical structuring. Similarly, in 2023, Herscher and his associates developed a neurovector symbolic architecture, blending vector-based symbolic computations with deep learning to enhance AI's ability to reason and generalize. These hybrid models are increasingly used in practical applications that require both structured reasoning and adaptive learning. For example, neural networks often act as black boxes, making it hard to understand their decisions. To rectify the situation, symbolic reasoning can add human-readable explanations to deep learning models. The debate between symbolism and connectionism has shaped AI's evolution, but the future may not belong to one over the other. As AI systems become more sophisticated, integrating both approaches offers the best of both worlds, combining human-like reasoning with the flexibility of machine learning. Whether AI is solving complex scientific problems or generating art, the synergy between these two schools will likely define the next frontier of artificial intelligence. Thank you for watching.